All right, so all right, this was in the video that I had you guys do over the weekend, but essentially with simplifying radicals when you include variables or radicals that are not square roots, instead of finding perfect squares, you're finding perfect cubes, perfect fifths, things like that. Or in other words, they're basically in pairs or sets, however many the index is. All right, so you can do this of either two ways. You can do it in terms of factor trees and break it down to its prime factors, or you can do it until you find either a perfect cube, perfect square, perfect fourth, perfect fifth, whatever it's asking for. All right, so let's do letter A first. All right, so I just like to break it down one part at a time. So I just do every little piece individually. So I do the number by itself, I do each variable by itself, because it's all going to go back under the same radical. So that's kind of how I split it up. Okay, so first off, it's a square root. So that means we're looking for sets of what? 2. All right. So first off, 36. We know that's a perfect square. So what is it? 6. We're going to go ahead and take that out from under the radical. I'm going to leave some space, and I'm going to put the radical back over here. Now, a to the 17th. So remember, since we're dealing with perfect squares, any multiple of 2, any exponent that's a multiple of 2, meaning that it can be divided by 2 evenly, is a perfect square. All right, when it comes to exponents. So like x squared, x to the 4th, x to the 6th, x to the 8th, those are all perfect squares. Now, a to the 17th, 17th is an odd number. So we'd have to split it apart into its closest even exponent and then whatever's left over. So what's the closest exponent to a to the 17th that's even? 16. So this would be a to the 16th, and what do I have left over? A. Now, what you have left over is automatically going to go back underneath the radical. All right. Our perfect square is a to the 16th. So if I took the square root of a to the 16th, who remembers what I said you have to do? Basically divide the exponent by the index. So divide 16 by 2. What is it? A to the 8th. So that's what goes on the outside. We're going to do the same thing for b to the 9th and c to the 7th. So for b to the 9th, what's the closest even exponent? 8. What I have left over? B. So b goes under the radical. What's the square root of b to the 8th? B to the 4th. Just divide that exponent by 2. And then lastly, c to the 7th. How do I break it apart? C to the 6th and c. So the c goes back under. What's the square root of c to the 6th? C cubed. And then that's your answer. So that's how I think about it, guys. I just do one part at a time. So I do the number by itself. I do each variable by itself. And then you just combine everything at the end. All right, let's try one that's not a square root. So let's look at letter E. So this is a cube root, meaning we're doing everything in terms of perfect cubes or in terms of sets of 3. All right. So again, I'm going to do each part individually. So I'm going to start with a 24. So with numericals, you need to break it down into either finding the nearest perfect cube or just break it down to its prime factors. I'm going to show you the prime factor method first because in my opinion, that's a little bit easier than just trying to shot in the dark break down to find a perfect cube. All right. So 2 factors of 24, let's just say I pick 2 and 12. All right. Which one of those two numbers is prime, meaning it can only be divided by itself and 1? 2, so I'm going to circle it. 12 can be broken down, let's say, to 2 and 6. And then 6 can be broken down to 2 and 3. Both of those are prime. So in other words, when the bottom of my branches are all prime, I know I'm done. Now, we're looking for a number that repeats 3 times. What number is that? 2. So guess what? You got your perfect cube right there. And the beautiful thing is that essentially if you did 2 times 2 times 2, that's 8. We know 8's a perfect cube. So if we took the cube root of that, we only need one of them. And that's what we pull out. So the 2 comes out. What we have left over is whatever number that we have, or numbers, that's prime, that's left. So that would be the 3. And that goes back under. So essentially, when I find the group of 3, I just take one of the numbers because that's essentially doing that cube root. Because remember, 2 times 2 times 2, if I take the cube root of that, I only need one of those 2's. That's the same thing as taking the cube root of 8. The other way you could have done it is you could have just found the nearest perfect cube. So you could have done it by 3 and 8, rewrote it as the cube root of 8 times 3. So that's the cube root of 8 times the cube root of 3. Still get to cube root 3. Either way would work. So it's just a matter of whatever you're comfortable with. If you want to find the perfect cube, that's fine. Just know that it can get dicey. All right. Now, x to the 5th. So, with x to the 5th, remember, since we're dealing with cubes, that means we're looking for multiples of 3. So what's the nearest multiple of 3 to x to the 5th? Too high. Has to go lower. X to the 3rd. So it has to be lower than x to the 5th. So if I break it up to x to the 3rd, what do I have left over? X squared. All right. So this goes back under the radical. So this would be x squared. What's the cube root of x cubed? X. So that's what goes outside. Then y the 7th. What's the nearest multiple of 3 that's lower than 7? Y the 6th. And we have a y left over. So the y goes back under the radical. What's the cube root of y the 6th? So remember, just divide 6 by 3. Y squared. So that's the same thing as dividing 6 by 3, so this will be y squared. And we're done. Any questions on this stuff, guys? Do I need to do one more? I'm just showing both ways you could do it. So you can either do it with the prime factors or you can do it by finding the perfect cubes. It's pretty much the same method, just different ways of seeing it. All right, does anyone need to see me do another one? Are you guys good? Yeah, I can do C. All right, so C, 4th roots. All right. So that means we're looking for perfect fourths. Let me ask you this. Is 81 a perfect fourth? If I raise a number to the 4th power, I get 81. Yeah, 3. So automatically 3 comes out. Now, x to the 4th, is that a multiple of 4? Yes. So if I take the 4th root of x to the 4th, what do I get? X. Y the 12th. 12 is a multiple of 4. So if I take the 4th root, what do I get? Y cubed. And that's it. It was a perfect fourth. So the radical just is gone. So if everything under the radical is a perfect whatever the index is, the radical doesn't exist anymore. It's just like if we said, if we took the square root of 4, it's 2. All right, the radical doesn't exist anymore. Any other questions? All right, you guys good on this? Okay. All right, so for the warm up, check your answers real quick. Are there any that you guys want me to go over? All right, I'll do one first. All right, so number one. So we have two radicals that we got to take care of. So the first thing you're going to do is get one of the radicals on the other side. So we're just going to add this 3 square root x to both sides. So this is the square root of 6x plus 3 is equal to 3 square root x. Now, even though we got this multiplying by 3 here, it doesn't matter. We can still go ahead and square both sides. We just got to make sure that we invoke the power rule. All right. So once you get both radicals on the same side, and you can't do any other simplifying, just go ahead and square both sides. So this radical completely goes away. This will be 6x plus 3. Now, the power rule gets invoked on the right side. So we have to make sure that we square the 3 as well as the square root of x. So in other words, we end up with 3 squared, and then the square root and the square cancel each other out for the x. So this will be 6x plus 3 is equal to 9x. So then I'll subtract the 6x over to the other side. 3 is equal to 3x. And then divide both sides by 3. X is equal to 1. And remember, you need to check for extraneous solutions, meaning it's a solution that even though you got it, it doesn't make the statement true. So if I do a quick plug in back in, 6 times 1 is 6, plus 3 is 9. Square root of 9 is 3, times square root of 1 is 1, times negative 3, that's negative 3, so that's 3 minus 3, which is 0. So it works. Any other questions on that one? All right, number 4. Yeah. Okay. All right, so this one has a little bit to it. So we cannot do anything with this 3 negative over here. So we just have to go straight into squaring both sides. Now, here's the thing. The left side's an easy square because this just cancels, we get x minus 3. The right side, however, this is now a binomial that we're squaring. So when we did polynomials, it's not technically a polynomial, but same concept. This is the same thing as 3 times negative square root of x times 3 minus the square root of x. So we can't just square them individually because of that minus in between them. If it was multiplying, we could do like we did in number 1. But since it's subtracting them, we got to do it like this. So my recommendation is do a very quick box method. So this would be 3 minus the square root of x, 3 minus the square root of x. 3 times 3 is 9. 3 times negative square root x is just negative 3 square root x. Still negative 3 square root x. Now, if I do negative square root x times negative square root x, what do you think I'm going to get? Positive x. The square roots will cancel out, the negatives will cancel out. If I pull everything out, this would be 9 minus 3 square root x minus 3 square root x plus x. Now, the nice thing is that these is kind of like combining like terms. So since they both have a square root of x, we can just add the coefficients in front of them. So this will be x minus 3 is equal to 9 minus 6 square root x plus x. Now, we need to get the square root by itself again. So I'm going to subtract the x to both sides. That goes away. That goes away. I get negative 3, 9 minus 6 square root x. I'm going to subtract the 9 over. That's negative 12 minus is equal to negative 6 square root x. And then divide the negative 6. So that's positive 2 equals the square root of x. So what do you think my last step is? Square both sides. So 4 is equal to x. If I did a quick check to plug it back in, 4 minus 3 is 1. Square root of 1 is 1. Square root of 4 is 2. 3 minus 2 is 1. So it works. So that one just had you do a little bit extra with it. And in reality, you had to square it twice. Any questions? Any other questions on this? Are there any other ones you want me to do? Or you guys go with the fractional exponents? Speak now, forever hold your peace. 6? All right. This is my last one. We got to move on. All right. So first things first. We got to get it so whatever is being raised to whatever power is by itself. So we need to add the 8. So this would be x minus 2 raised to the 3 halves is equal to, Claire, do you mind shutting that door, please? 64. Thank you. Now, what did I say you need to do to undo a fractional exponent? You raise it to what power? It's reciprocal. So the next thing we're going to do is we're going to raise both sides to the what power? 2/3. That's a reciprocal of 3 over 2. That goes away. Now, if we did a quick conversion of 64 to the 2/3, you could either put that in your calculator or you could do the cube root of 64 and then square it. Cube root of 64 is 4. Square that, 16. X minus 2. Add the 2 to both sides. X is equal to 18. And I can assure you, if you plug that back in, you get the correct answer. Mm-hmm. Sure. All right. 2 is honestly not bad. It just turns into a quadratic. So square root's already by itself, so we can square both sides. Now remember, x minus 2 squared, you have to do x minus 2 times x minus 2. So you either need to FOIL that or do a quick box method. So this will be x is equal to x squared minus 4x plus 4. If we subtract the x to the other side, we get x squared minus 5x plus 4 is equal to 0. And then we do a quick factor. So if I factor it, what are 2 values of 4 that multiply to give me negative 5? Or add to give me negative 5, sorry. Negative 4 and 1. So this will be x minus 4, x minus 1. Set both equal to 0 and solve. You should get x equals 4 and x equals 1. Now, remember, extraneous solutions, you need to double check and plug them back in. So if I plug 4 in, square root of 4 is 2. 4 minus 2 is 2. If I plug in 1, square root of 1 is 1. 1 minus 2 is negative 1. So 1 is not equal to negative 1, so that gets thrown out. So I'm left with x equals 4. So you always got to check because they will throw an extraneous at you.
Didn't you say that we check both solutions just in case they're both extraneous?
Yeah, it can happen that both are extraneous. So you can't just assume if one of them's extraneous, the other one's correct. Both can be extraneous. It's happened before. All right. So, any questions on simplifying or solving? All right. So, let's get into what we're doing today, which is operations. So, we've already done some operations before back in Unit 4, but now we're going to expand on that. So, now we're going to throw in the variables. So, this kind of applies what we did, or what I had you guys do over the weekend with 5.4, as well as what we did way back in Unit 4 at the beginning of it. All right. So first off, we're talking product rules of radicals. All right. Now, they got to be non-negative real numbers, A and B. As long as you're multiplying the same radical type by the same radical type, meaning square root times a square root, cube root times a cube root, fourth root times a fourth root, you can just combine them under one radical and multiply them together. So for example, if I do square root of 50 times square root of 2, what's that equal to? The square root of 100. I just do 50 times 2. What's the square root of 100? 10. If I do number 5, this is the same thing as 10 times 20. So that's square root of 200. How can I simplify square root of 200? 2 times 100. So this would be the same thing as 100 times 2. So what's that equal to? 10 square root 2. Square root of 100 is 10. You're left over with the square root of 2. All right. Look at number 6. Okay, they're both the same type, so I'm just going to rewrite it as just multiplying under one radical. This will be 5x cubed times 5x squared. So this is where exponent rules get thrown in. So first off, you want to simplify what's under the radical first, and then you can simplify the radical itself. So remember, coefficients you just multiply together like normal. So what's 5 times 5? 25. Now, what do I do with the exponents? Add them. So x to the what? 5th. And now I can simplify. So if I do 25 first, is 25 a perfect square?
Yeah.
Yes, what is it? So I'm going to pull the 5 out. Leave myself a little space. X to the 5th, is that a perfect square? No, but what could I break it down into? 4 and 1. So x to the 4th and x. So the non-perfect square goes back under the radical. And then what's the square root of x to the 4th? X squared. So that's what goes outside. And you're done. Any questions so far? All right, walk me through number 3. So since we have coefficients on the outside, we just multiply them like normal. So what's 5 times negative 4? Negative 20. And then we multiply what's under the two radicals. So what's 8 times 8? 64. Now, what's the square root of 64? 8. So this is now negative 20 times 8, which is what? Negative 160. Any questions with the square root aspect? All right, let's look at non-square roots. Let's look at 7. So now we're dealing with what type of root? Cube root, so pairs of 3. So we're going to do the multiplication first. So if I do some multiplying, so I'm just going to rewrite everything in terms of multiplication under one radical. So 9 p squared q squared times 6 p q squared. So it just looks like we're simplifying exponents using the product rule. It's just all underneath the cube root. So what do I do first? 9 times 6, which is 54. Then add the p squared to the p the first, so that'll be p3. Right, then 2 plus 2 is 4, so this will be q the fourth. Now, don't assume that that's your final answer. I always want your radicals in simplest form. So we need to simplify each aspect individually. So 54. Do you guys want to do the prime factor method or do you want to do the perfect cube method? All right, I'll do prime. Okay, 54. I need 2 factors of 54. 9 and 6. Are either of those prime? No. What can I break 9 down to? What can I break 6 down to? So, all 3 of the, or all 4 of those numbers are prime. What's my group of 3? The 3s. So what gets pulled out? A singular 3. So we only need 1 from the group to come out. What's left over? A 2. And that's what stays under the radical. Now, p cubed, is that going to be a perfect cube? Yep. What's p cubed cube root? P. So that just comes out of the radical, and there's no p's under the radical. Q the fourth, is that a perfect cube? No, but what can I break it down into? Q3 and Q. So in other words, the closest exponent that's a multiple of 3, and then whatever's left over. So the Q goes back under. And then what's the cube root of Q cubed? Just Q. So that's your answer. Try number 8 on your own. So be careful, it's a 4th root, so try that one on your own. So you're looking for groups of 4. That's just another way to write multiplication. So remember, parentheses times parentheses, just multiplying. You just wrote a different way. So start with the multiplying and then simplify after. Mm-hmm.
I don't know what the way to find it.
Basically whatever's left over. So like just circle your You could if you wanted to, in reality. So whatever's left over. Once you All right, y'all. Check your answer. So this is what I got. Now, something that some people were asking me is when you do your factor tree, they ask, okay, what happens if you have more than one number left over? What you do is you just multiply them back together. So if you notice, I had these two twos left over. I multiplied them back together, and that's what created that 4 right here. All right, so once you get all of your sets that you need, so all your sets of 4 that are there, which was only one, it was the 2, you take whatever's left over, multiply it back together, put it back under the radical. So everything has to go back under the radical that's left over. All right, any questions on this one? All right, now, the next part is the adding and subtracting radicals, which is very similar to combining like terms. So just to review, what would my answer be for this one if I combine like terms? So it'd be 5x. So 2x minus x, remember you're just adding or subtracting what's in the coefficients. So 2x minus x, that's the same thing as 2 minus 1, which is just x. X plus 4x, that's the same thing as 1 plus 4, which is 5. So this would be 5x. What about this one? So the 2x, we just bring it over because there's nothing combined. And then 3y plus y is 4y, minus 6y is negative 2y. Now, why are we talking about combined like terms? Because again, it comes back here. So, adding and subtracting radicals. All right, so remember, when it comes to combining like terms, think just polynomial for a second. So like what we just did up here. When it comes to combining like terms, how do we know that we can combine those terms? It has the same variable and the same what? Exponent, yeah. So, same variable, same exponent. Similar thing here. So when you add or subtract radicals, you can only do so if they contain the same index and radicand. Now, we talked about this last week. What's an index? It's the number outside the radical. So in other words, if I had a cube root, my index was 3. What's your radicand? the value that's underneath the radical. So let's say I had a 27 here. That's my radicand. All right, so you have to have the same number in the index, same number or value under the radicand in order to combine. Now, just like how we don't change the variable expression when we add or subtract, we're not going to change the radical expression either. So in other words, anything under the radical stays the same. We only add or subtract the coefficients of the numbers in front of the radical. Now, we can change things to look like they have the same value under the coefficient, but we'll get to that in a second. Let's look at number 1. First off, we got to ask ourselves, do we have the same index? Do we have the same number under the radical? Is that true? So for each of these, do they both have the same index and do they both have the same number under the radical? Yes. All right. So since that's true, all we're going to do is our final answer is going to contain the square root of 2. And all we're going to do is add those two numbers outside of the radical. So what's my answer? 13 square root 2. All right. What about number 2? Do I have the same index and number under the radical? Yes. So index is 2. Number under the radical or radicand is 3. So I can just add my 3 numbers here. Remember, this is -1. So my final answer is going to contain the square root of 3. -1 plus 5 is 4. Minus 10 is what? -6. And that's it. Now, look what happens when we look at number 3. So, we have one that does not have the same radicand, but that's okay because we only need to combine the ones that do. All right, so just like if we did like x squared plus 2x plus x, we would just combine the x's and then we bring down whatever's left over. So we would start by bringing down the square root of 3, and it's negative. Now, if I add the 4 and the -1 together, what would I get? Plus 3 square root what? 5. And it's okay if you leave that as an expression, as long as it's brought down to its simplest form. Now, look at number 4. These are kind of all by their lonesome. They don't have anything we can combine, but what do you think I can do to those radicals? Could we possibly simplify it down to where we get something with the same radicand? Yes. So, let's just think about this for a second. We're talking about square roots of pairs of 2. Does 10 have any perfect squares in its factors? No. So this is probably left alone. What about 40? Does 40 have any perfect square factors? 4 and 10. Where 4 is the perfect square. So if I rewrite this, this will be -7. It's the same thing as 4 times 10. Well, what's the square root of 4? 2. So this will be the same thing as -7 times 2 square root 10. So this will be 2 square root 10 minus 14 square root 10. And just like that, we now have the same number as the radicand, so we can combine the like terms. So what's my final answer? Negative 12 square root 10. So if they don't have the same numbers under the radicand, try simplifying to see if you can make it so it has the same number under the radicand. But be careful, because whatever you pull out of the radical, you need to multiply it to whatever coefficient's already there. Any questions so far? All right. Try number 5 on your own. So simplify the radicals and see if you can get it down to the same. So start by simplifying the radicals that look like they can be simplified. All right, so someone raise your hand. Tell me what you got. 11 square root 2. Good. So that's exactly what I got. Now, just from walking around the room, the biggest mistake that I saw is that whenever you simplified the radical, you forgot to multiply whatever you pulled out by the number originally in front of it. That's usually the biggest mistake I see with these. You cannot forget to do that. So my suggestion is, when you rewrite your radical, go ahead and bring that number down first and leave a little space. I simplify the radicals. So I broke 18 down into 2 and 9. Square root of 9 is 3. Pull the 3 out, left with the 2 underneath. All right. Now, look at number 6. So we got the same radicand, but why can we not combine them? They don't have the same index. This one's an index of 2. This one's an index of 3. So we can only leave this as this. There's no combining. It's done. Now, all right, number 7. Got to do a little legwork here. So first off, let's simplify these radicals. So if I look at the 2x squared, is the 2 going to simplify down any further? No. So we're going to keep that down there. Make sure you put the 5 on the outside. What about the x squared? Can I simplify that? Yeah, what's the square root of x squared? X. So I have 5x square root 2. What about 200? Can I simplify that down? What's the perfect square in 200? 100. I'm left with a 2. So what gets pulled out? 10. And make sure you bring down that negative 3x. What's left under the radical? 2. This will be 5x square root 2 minus 30x square root 2. They got the same radical, not the same radical, the same radicand and index. So I can just combine the two like terms, which 5x and 30x are like terms. So this would be negative 25x square root 2. Yes, ma'am. 3 times 10. Yeah. All right, let's look at 10. So 10's a little different than what we've been doing. It's perfect cubes. But we can still simplify perfect cubes. So first off, 81. Do you guys want to do it the prime factor method or the perfect cube method? Okay. Yeah, because this one's pretty easy to find. So what's a perfect cube in 81? Nope. That's a square. 3 and 27. Which one's the perfect cube? 27 is. So what gets pulled out? What's the cube root of 27? 3. So this would be 3 cube root. There's a 3 left over. Is x a perfect cube? Could I simplify it further? Nope. Stays there. Minus 3x. We can't simplify that, so it stays. And then 24. If I simplify 24, what's the perfect cube in 24? 8. So guys, if the perfect cube method confuses you, then, 8's the perfect cube. But if that confuses you, just keep breaking it down till you got prime factors. Find which one repeats 3 times. So this would be 2 and 4, 2 and 2. These 2's repeat 3 times, so that's my perfect cube. And we already know that the perfect cube was 8. So this would be 2 cube root 3x. So now we got the same thing under the radical. So I can just add these together. Remember, there's an unspoken 1 here. So 3 minus 1 is 2, plus 2 is 4. So 4 cube root 3x. Any questions on that one? All right. Now, number 11 is a little bit different, but it's pretty much the same process. So, it says to find the perimeter of the triangle, give your answer as a radical expression. So if we're talking about perimeter, what does that mean we have to do? Add all three sides. So this is the same thing as 3 square root 20 plus 13 square root 5 plus 10. So the 10 is probably going to be something that's going to be left alone because it doesn't even have a radical. But which radical do you think I could simplify to try and see if it matches the other radical? 20. So what is 20? What's the perfect square in it? 4 and 5. 4 is the perfect square, so what gets pulled out? 2. So I have 3 times 2, which is 6. So 6 square root 5 plus 13 square root 5 plus 10. We can only combine the first two. This will be 19 square root 5 plus 10 millimeters. And we can just leave it like that. Because when I pulled this out, I would get the 3 still there, and then I pulled out a 2 from the 4. And I'm left with a square root of 5. So you have to multiply it to get the 6. All right, any questions on addition, subtraction? Now, advanced multiplication, I kind of talked about this a little bit with the example that we did with the warm-up. All right. So advanced multiplication, it's just same thing that we did with polynomials. Those multiplication rules apply. So like distribution, box method, those types of things. But it's with radicals instead of variables. All right. So for number 1, what do you think I'm going to do to that square root of 3 in the front? We're just going to distribute it. So this will be the same thing as the square root of 3 times 5. I don't know why I put 15. Plus the square root of 3 times 3 minus. Now, since 2 is not under a radical, we just keep it on the outside and just slap a square root of 3 next to it. So let's do some simplifying. 3 times 5? 15. Could I break down 15 anymore? No. 3 times 3, that's the square root of 9, minus 2 square root 3. Now, is there anything else I can simplify in there? Yeah, the square root of 9. So this will be square root 15 plus what? 3 minus 2 square root 3. Now, square root of 15 won't simplify anymore. Square root of 3 won't simplify anymore, so we can't combine any like terms, so we're pretty much done. I'm just going to rewrite this so that the non-radical number is in front. So this will be 3 plus 15 square root of it minus 2 square root 3. You could have left it like that in the green. I would have taken it, but just note that a lot of times they put that number that is not attached to a radical in front. Now, for number 2, box method is your friend. All right. So I would literally just set this up like either a box method or you can FOIL, whatever's you like best. I like box method because it's easier to see, especially with these. So 9 times 5, 45. Now, if you're multiplying a number that's not under a radical by a number that is under the radical, you just bring it to the outside and multiply the coefficients. So negative 1 times 5 would be negative 5, slap on a square root of 2. So 9 times the square root of 12, that'd be like 9 times the 1 in front of the square root of 12, which is 9 square root 12. Then 1 times negative 1 is negative 1. 12 times 2 is square root of 24. Does everyone follow what I just did? Then you just take everything out of your box and combine or simplify where you can. So it's be 45 minus 5 square root 2 plus 9 square root 12 minus square root of 24. Now I'm not done because I need to check to see if any of these can simplify down. So the square root of 2, probably not. What about the 12? What do you think? Right, we could break it apart into 4 and 3, and the 4 is the perfect square. So this breaks down to 9 times 2 square root 3. So this would be 18 square root 3. What about 24? 6 and 4. So pull the 2 out. This would be negative 2 square root 6. And I bring everything else down. Now, I simplified everything to its max. So can I combine anything? No. So we're done. Now, sometimes you can combine stuff, so that's why you can't just assume that you can't. All right, this was just one of those examples where you just couldn't. Now, number 3, I did an example like this in the warm-up with that one equation. This is the same thing as doing 2 plus square root of 3 times 2 plus square root of 3. All right, so if I do a quick box, 2 plus the square root of 3, 2 plus the square root of 3. So this would be 4, 2 square root 3, 2 square root 3. Now, if I multiply the same radicand by the same radicand, it's just the square roots cancel out, so we can just write a 3 there. You could do square root of 9, but just know it's still simplified down to 3. Save you some time. So if I pull everything out, 4 plus 2 square root 3 plus 2 square root 3 plus 3. What can I combine? The 2 square root 3's and the 4 and 3. I don't know why I highlight all that in the same color. There we go. So I would get 7 plus what square root 3? 4 square root 3. That's it. Now, last one. For this one, what does this look like to you if you were thinking polynomials? It kind of looks like a difference of squares. So let's see if it actually will do what a difference of squares does. So if I do a box method, this would be 4 minus square root 10, 4 plus square root 10. 4 times 4? Then negative 4 square root 10, 4 square root 10, square root 10 times negative square root 10. Negative square root 100, which is just negative 10. So this would be 16 minus 4 square root 10 plus 4 square root 10 minus 10. What happens right here? They cancel out because this would be 0 square root 10, which anything times 0 is 0, so that goes away. So I'm left with 16 minus 10, which is what? 6. Any questions on that advanced multiplication? So it's honestly not hard, it's just box method. All right, last thing, and then we're done. Rationalizing the denominator. So remember, we talked about this in the last unit. When you rationalize the denominator, we do not like square roots in the denominator. So does anyone remember what I have to do? multiply it by that, whatever's in the denominator. So for number 1, we multiply it by the square root of 5 over square root of 5. So this would be 2 square root 5 over what? 5. Then we check to see if we can simplify further. Can square root of 5 simplify further? Can 2 over 5 simplify further? So we're done. Shh. What about number 3? What do I need to multiply by? The square root of 10 over square root of 10. So this would be 30 square root 10 over 4 times what? 10. 30 square root 10 over 40. What simplifies? The 30 and the 40. So this will be 3 square root 10 over 4. Can I simplify the square root of 10 any? Nope. Only breaks down to 5 and 2. Neither are perfect squares. What about number 4? So even though it's a cube root instead of a square root, it's still the same process. You just multiply the top and the bottom by the cube root of 9. And just like with the square root, well, not quite like a square root. So here's the difference. All right. Cube roots, we cannot automatically cancel out the radical. All right. Why? You have to multiply it 3 times in order for that to work. So this would be the cube root of 9 over the cube root of 81. Now, here's my suggestion. Simplify the cube root of 81 first before you multiply another radical to it. Because otherwise you're going to have some really, really big numbers. All right, so if I simplify the cube root of 81, what are 2 factors of 81 where 1's a perfect cubed? Well, 9 is perfect squares. I'm talking 3 and 27. 27 is the perfect cubed. So this would be the same thing as the cube root of 9 over cube root 27 is 3, and you're left with the cube root of 3. Now I'm going to multiply the top and the bottom by the cube root of 3. So this would be the cube root of 27 over three cube root of 9. All right. Now, here's the issue. What's the cube root of 27? 3. All right. And then what happens? Yep. So we kind of end up starting with what we left off with. All right. Now, we're going to leave that there. Okay, because we only got about 10 minutes left. So we'll pick up with this last little bit tomorrow. Yep. We'll talk about 4 a bit more tomorrow. I just want to leave that. I'm just going to put a pin in that for right now. Say again. There's a Delta math that covers 5.4, 5.5. It's not going to be due till Wednesday. But I would at least try some tonight so that if you have questions, you can come to me with it tomorrow. Now, if you did not finish the homework from over the weekend, I'm checking that tomorrow. 22.